Okay, so in this video we're going to look at integration. So let's start out with a definition. In our previous videos we've seen that the first derivative, f prime of x, can have a notation like this. So the integral, or the antiderivative of this, can be given as so. This expression says that the integration of our derivative with respect to x is equal to our original function f of x. So this symbol here is called the integral sign, and the subject of integration can be referred to as the integrand. And the dx part is our variable of integration, so what we are integrating with respect to. And f of x is just simply our original function. So the integral of the first derivative with respect to x is equal to the original function, which leads to the name antiderivatives. So let's take a look at a couple of definitions first. So firstly, we're going to look at the difference between indefinite and definite integrals. And it's known as an indefinite integral because there are no limits to the integration. You'll see what that means a bit more when we look at a definite integral. So the integral of dx simply says the integral of 1 with respect to x, which for now I'll just tell you is equal to x, plus always our constant of integration. So this constant of integration represents every possible antiderivative value, and the reason for it being there is because the derivative of any constant is 0. So if we integrate indefinitely, we need to add the constant for it to be correct. Now if we look at a definite integral, in a definite integral we have limits on the integration, so there are often numbers depicted at the bottom and the top of the integration symbol. And in this instance, our integral is still x, however, we need to impose the range of the definite integral in our solution. So this is the same thing as saying x equals 0 and x equals 1. Which is also sometimes depicted in this sense, with a straight line at the end. And what that means is we need to substitute the values. So in this instance we need to substitute our x equals 1 value into our solution. Quite simply, in this case, it's just equal to 1. And then from that, we subtract the bottom value, where x equals 0 in this instance is just equal to 0. And when it comes to definite intervals, you always have the top value substituted, subtract the bottom value substituted. Okay, so with our values of integration defined, there are also some rules of integration. Just like the fundamental rules of differential calculus that we saw in the previous videos, there are rules for antiderivatives. So let's take a look at the reverse power rule. The reverse power rule says that x to the nth power integrated with respect to x. And in the power rule of differential calculus, what we did was we multiplied by the old power and then reduced the power by 1. In the reverse power rule of integration, we need to increase the power by 1 and then divide by the new power. So we have x to the n plus 1 divided by the new power n plus 1. And as always, with this being an indefinite integral, we need to add a constant of integration plus c. So for example, the integral of x cubed with respect to x is equal to increase the power by 1, so we have 4, divided by the new power, so 4. And as always, our constant of integration c. As well as a reverse form of the power rule, there's also a reverse form of the chain rule. So for example, if we had the integral of the cosine of some value nx, its integral with respect to x can be found using the reverse chain rule. So in differential calculus, what we did was we differentiated the cosine part, and then we multiplied by the derivative of the inside of the bracket with respect to x. So in this example, what we're going to do is find the antiderivative of cosine and then divide by the derivative of what's inside this bracket. So since sine differentiates to cosine, it must mean that the integral of cosine is equal to sine. We still have our nx, and then instead of multiplying by the derivative of what's inside the bracket, we need to divide by the derivative. So in this example, the derivative of nx with respect to x is just n. And as always, with our indefinite integral, we need to add a constant of integration plus c. So now let's put our skills to the test and look at a more complicated example. So we can see here that this is a definite integral evaluated between the points x equals 1 and x equals 2. We also know that we can apply the sum rule. So similar to differential calculus, our sum rule said that the derivative of a sum of functions is equal to the derivative of each of the functions summed together. So the same is true in integral calculus. So the integral of a sum of functions is equal to each individual function integrated, summed together. So firstly, let's split this up. So this is equal to 3 times the integral of our e to the x with respect to x between x equals 1 and 2 minus seven times the integral between 1 and 2 of 1 over x dx, which can be written as dx over x, plus 2 times the integral between 1 and 2 of x squared with respect to x minus 6 times the integral between 1 and 2 of 1 times dx, which is just dx. And the reason we can pull the constants out in front of the integral symbol is because they will always multiply by the end result. So, for the first part we have here in yellow, we know that the derivative of e to the x is still e to the x. So the antiderivative, or the integral, of e to the x must still be e to the x. So we still have the 3, and then we have the integral of e to the x, which is equal to e to the x, and we still need to evaluate this point between 1 and 2. Subtract, and in blue we still have 7, and we know that the derivative of the natural log of x is equal to 1 over x, So therefore, the antiderivative of 1 over x must be equal to the natural log of x evaluated between 1 and 2, plus the part in green, we have 2 times, and as we saw earlier in the reverse power rule, x squared, so we increase the power by 1, so we have x cubed, divide by the new power, and then we still need to evaluate that between 1 and 2, and then again subtract 6 times the integral of 1 with respect to x is simply x, because this is equal to x to the power of 0. So what we're doing here is increasing this power of 0 to 1 and dividing by the new power, which is 1. So we have x to the 1 over 1, which is just x, evaluated between 1 and 2. So finally we have 3, and now it's just a case of simple substitution. So we always substitute the top one and then subtract the bottom one substituted. So we have e to the 2 subtract e to the 1 minus 7 times the natural logarithm of 2 subtract the natural logarithm of 1 plus 2 times, and if we substitute 2 into here, we have 2 cubed, which is 8, divided by 3, subtract 1 substituted into this expression, so 1 cubed is 1 over 3, so 8 thirds minus 1 third, and then finally we have subtract 6 times, quite simply 2 minus 1. So finally, to simplify this off, we have 3 times e squared minus e, which can't be simplified, subtract, and we know that the natural log of 1 is equal to 0, so we have 7 times the natural log of 2, plus, and 8 thirds subtract 1 third is 7 thirds, multiplied by 2 is 14 thirds, and then 2 minus 1 is 1, times 6 is minus 6, and there we have our final solution. So hopefully this video has been a good introduction to integral calculus, and in the next video we're going to take a look at some more of the tricks we can use. So we're going to take a look at integration by substitution to solve some trickier integrals. And as always, if you have any questions or comments, feel free to pop them in the box below. I'll see you in the next video.